So thanks Arno and Matt for the two sessions in the morning, and I think you've give a very good introduction on DFT, especially the settings and how to submit jobs. So for this session, I would just give you probably a very brief introduction on molecular dynamics, and then I think I will leave a large part of time on practical sessions so that you can practically submit job and analyze the trajectory data. So basically, can you see my slides at the moment? Am I clear?
Yes, we can. They are not full screen, so we're seeing your sidebar and everything as well.
Yeah.
Now they are. Yeah.
Yeah. So okay. So basically, the session will be organized like this. Firstly, in brief introduction, and then I will talk about the ab initio molecular dynamics of one of my work as an example, and then the rest of time will be practical sessions on job submission and running and data analysis by using both DFT to evaluate the force and the neural network potentials. And these are pre-trained files. I've done the training, so and because it takes some time, you won't be able to do it in such a short period of time. You can use the pre-trained models to do a molecular dynamics simulation. Okay, so basically a molecular dynamics is a simulation that trying to simulate a motion of our atoms by solving equations of motion. Because if you're doing DFT simulation, it gives you a equilibrium normally. If you do relaxation, give you equilibrium positions, and you can also do single point calculations on geometry. But in reality, the atoms are always oscillating or moving, and a lot of properties. If you want to simulate and calculate them, you have to simulate the motion of the atoms. We are doing this by solving the equation of motion. Basically, it's just for example, using Newton's law to calculate the position, the force the atoms are felt in, and the velocity, for example, and by calculate time in a very small time step, and we write this information into trajectory files, and so that later on we can calculate the properties based on the trajectory files. So I'll only give very brief introduction to ensembles and thermostats and later on, because I'd encourage you to refer to previous materials training that gave much more details on the on these on ensembles and also thermostats. So basically, ensemble is a all microstates accessible to simulation, and they are associated with a probability. And later on, if we do averaging over this each frame or image, and then we will get a ensemble average of that property. And we can have different options to fix in the simulation. For example, we can fix the number of atoms, the volume and energy, which is a completely isolated and micro-canonical system where the energy is conserved. And we can also fix the number and the volume of the system and also the temperature. But in practical, this is achieved by a heat bath that exchanges energy with our simulation cell. And this means that the total energy of the system itself is not conserved, but instead the energy is conserved by adding the system and the heat bath. And we can also say allow the cell volume to change, and by fixing by put the system under a constant pressure, but this will not be a constant pressure. Again, this is controlled by a biostat, and that your pressure will change a bit, and at this is a circumstance that the quantity that conserves is the energy of your system and the heat bath and the biostat. So we can set up our chosen ensemble like this by putting this by keyword and value. We can change it to any of these listed here according to your requirements. And okay, so we have talked about in practical, we'd mostly use an ensemble like to produce our trajectory like MVT or MPT. So basically we control the temperature by thermostat. Again, I wouldn't go into a very detailed theory about this because you can always refer to, I have for the reading slide, you can refer to the contents there if you are interested to know more about this. So basically we have different thermostats. We can set it in the input script here, and most importantly, we, for example, we have to set up the time coefficient, time con here, and this determines how frequently your system exchanges energy with either thermostat or biostat. So and there are some tips for setting up this parameter, and normally the default value is okay, and but you have to check the one of the output file I will mention. Will talk about later, so that we know that the simulation goes well, especially if you're doing a simulation on a new system that's not familiar to you. So basically, after you submit the job and run the simulation, you will get a list of trajectory files on position, velocity, force, and if you write out the stress tensor, you will also have this file, and you would always have this file for you so that you can continue your simulation where you stopped. And you also have this file, which is very important, that contains information on how if your simulation, for example, the constant of motion is conserved or not, and if you will get some parameters written into this file. So to control the print frequency, because if you set a time step like 0.5 femtoseconds, it will be so if you print every step, the change will be very small. So normally you would set up, say, like 10 write a trajectory write a image every 10 steps. So for example, I would recommend you to set the cell print frequency same as your trajectory, so that you will see this will be a benefit if you are preparing input reference data for machine learning potentials. Because these are matched so that you can directly extract the data from these files. Okay, so force evaluation, we have different options. For example, the DFT method, which you've had a practice on this morning in this morning, so that the settings is really depending on your system, and also when you're doing molecular dynamic simulation, you would also consider the efficiency. So you will use the fastest settings so long as the accuracy is acceptable, because normally you would run very long simulations, and it can take a very long time. And you check the menus for all the options, and I think you've got a good idea on how to set up this from the sessions in the morning. So I wouldn't go to details. So okay, so basically after you run the simulation, for example, you are doing a equilibration of your system, you want to know if the simulation goes well, you have to check out this file, and you can either use Notplot, which is already installed in ARCHER2. Alternatively, you can use Jupyter Notebook. I will show how to use Jupyter Notebook to pull out this file, because I will also incorporate a visualization of the trajectory in that notebook as well. So almost every data analysis I've talked in this session can be achieved by using just Python and Jupyter Notebook. So if your simulation does not work well, you have to go back to, say, make your convergence criteria tighter, and for example, to decrease your time steps, and also play with this parameter. Okay, so I will. So normally you wouldn't be able to finish your simulation if you're in one job, because normally the HPC will have a time limit on your job length on the wartime your job is running. So basically what you can do is just to add this into your input script and change your settings especially if the first step is equilibration, and you like to change your ensemble or other settings, then you would make changes in your input script, and alternatively you can directly copy this restart file as a new input script and submit a job, and it's also fine. Okay, so basically analysis, there are a bunch of packages that are available for different purposes. So if you trajectory visualization, you can use VMD and GLView. For example, this one's highlighted are Python based, and MD traject. And if you're, for example, want to calculate the vibration spectra, then you would normally use Travis, which is has a tutorial on CP2K documentation site. So if you are calculating that, refer to that tutorial. I think it's fairly straightforward. And okay, here I will give you an example of previous simulations. So basically, the system is two supramolecular cages that are synthesized by using these two smaller molecular cage reacted with trifluoroacetic acid. So the system has a very big. So this a single unit cell has about 600 atoms inside it. So I'm interested in how what molecules are diffused are moving inside these cages. As you can see, these are, although they start from similar molecular cages, but because the molecular cage has different pore size, it resulted in very distinct structures of the supramolecular cages. One is more like a plum pudding structure where the TFA anions are located inside the pores and outside, and is scattered everywhere inside the supramolecular cage. And the other one is more like a sandwich structure because the TFA can't be accommodated in the small pore of the molecular cage. So it forms two layers of the molecular cage, and the TFA anions are located in between. So it forms a layer of TFA chains between the molecular cage. And there are also water molecules inside the cage and supramolecular cage that are moving. So we'd like to know what the difference of the diffusion coefficient, for example, and also the reason why, if there are diffusion coefficient difference, why they're different. So we did a very long ab initio molecular dynamic simulation using CP2K, and basically these are our input settings. I've just included key settings here, for example, thermostat and time con, and also we're using the OT method. You should have built up an idea on what this is because Matt have introduced this in this morning, and because our system is big, I'm not using full OR. Instead, I'm using full single inverse in the preconditioner keyword setting here. And then we are also include the vent valves potential so that the intermolecular forces are more accurate. So the data analysis is Python based. So basically it's Fishmole, which is developed by ourselves, and also ASE. So basically we calculated the diffusion coefficient using original trajectory because and then we also did hydrogen bond analysis using the trajectory that all atoms are wrapped within the simulation cell. So basically we recognized hydrogen bonds and did calculated the radial distribution function and angular distribution function, and also plotted out combined distribution function. You will find out how this is useful to find out the behavior of hydrogen bonding. And also we calculated hydrogen bond lifetime based on a time autocorrelation function. So basically, we did simulations under different temperatures, and these are the diffusion coefficient under, I think this is 500K. We did different, we calculated the diffusion coefficient under different temperatures, but these ones are, I think, is 500 Kelvin. And we found that cage 1, which is with the TFA located everywhere inside the pores of the molecular cage and outside the pores of the molecular cage, have a diffusion coefficient about 4.5 times larger, and it also have a smaller apparent activation energy. But according to experimental measurements, cage 1 is 100 times more proton conductive. So we did analysis on the diffusion coefficient and anisotropy by calculating the diffusion dimension diffusion coefficient along different directions, which is just a mesh grid of directions. And we found that cage 1 has much smaller neck, as you can see in the diffusion coefficient of 1 dimension diffusion coefficient compared to cage 2. And if we split the supramolecular cage into channels, and we would see that cage 1 along the most diffusion, if we split, if we say define the direction with the most high diffusion coefficient as the channel, and this direction with the smallest one diffusion coefficient, we split it into different channels. We will see that for cage 1, almost all water molecules can switch channels, but for cage 2, almost all water molecules stay in the same channel. That explains why, although we didn't see a huge difference on the average 3-dimensional diffusion coefficients, but experimentally they have cage 1 has much larger diffusion coefficient. And also considering the experimental measurement based on a polycrystalline sample, there will be a high density of grain boundaries that can stop the diffusion from the from the direction with the highest diffusion coefficient. And then we analyzed the hydrogen bonding using the geometry criteria, which is listed here. So basically, it's just the separation between the donor acceptor and this angle. If this is almost 180 degrees, then it's very strong, and if it's short, it's very strong. So there is we recognized all hydrogen bonding within the supramolecular cage of each frame of the trajectory and plotted the density out. If you can see, this is the separation of donor acceptor, and this is the angle, this angle. And if you compare these two distribution, you would see that they have very similar location and dense in the separation angle plot. which means they have very similar strength and they are moderate strong in terms of the dissociation energy. And we also calculated the lifetime based on the time autocorrelation function, which just counts, set a reference frame and count the number of hydrogen bonds. And we count it again after a certain period of time and see how much are still bonding and calculate the averaging of the every reference frames. So it basically a exponential decay, and the lifetime is the lifetime of the fitting exponential function. So and also we calculated the hydrogen bond numbers on water, because we're interested in the water diffusion, and we found that on average in case 2 there's one more hydrogen bonding on the water molecule, which resulted in a much longer hydrogen bonding lifetime. This explains why it moves. It's more difficult to move around in supramolecular cage. So we also use the combined distribution function to study the behavior of the hydrogen bonding. So if you plot the RDF radial distribution function and angular distribution function together like this, you will find that hydrogen bonding have a distinct peak here around the bond length and bond angle, and you also have some dispersive features moving, indicating that in some frames the water molecule are moving around. So if you plot out different functional group with water, for example, with different donor and acceptor, you can find out the behavior difference. For example, these are very distinct peaks, indicating these are very strong hydrogen bonding, but these are less distinctive, and sometimes you can have other peaks at lower angles because they have alternative geometry, and there are a lot of dispersive features indicating this is less strong compared to that one, like here, like this hydrogen bonding. Basically, there are different functional groups, and we also found an interesting thing that the water can clustering inside the supramolecular cage and forming this twin peak combined distribution function. And this is an interesting discovery because for high proton conductive materials such as naphthalene, this water diffusion is relied actually on the clustering inside these materials. So this means by a reasonably design of the supramolecular cage, we can in principle achieve very high proton conductivity like naphthalene. And this is what we've done using AIMD, using CP2K, and I've introduced the data analysis. Now we will do some finally practical session. So before we start the session, I'd like you to copy the data from this directory. And sorry.
Yes, there's a couple of messages in the chat. One question and maybe a comment. Would you be happy to have a look now? It might be a good point before the practical. I can read I can read it out if you like, or would you like to have a look at the chat yourself?
So which ones are?
Comment from Martin, 2 comments from Martin, with a question from Maxime in between.
So is this calculative substitution? So is this one is already answered, or?
Well, if it's, I don't know if it's clear, but if Martin, would you like to unmute your mic and you could actually ask directly or comment directly?
Okay. I suggest to use MVT. First, you can try to use MPT. Yes, to relax structure. Yes, to zero stresses, and after that fixed or take average volume and perform calculation with MVT. Generally, calculation with MPT are much more difficult than MVT, because you have to control pressure and temperature, and it's like this, that to get pressure convergent, you need, I don't know, maybe 100 or something like this, longer calculation, because it's generally difficult. And devil is in details, because in MPT you can do relaxation in different way, because you can allow vibration as a whole, is isotropic or anisotropic, and all matters. So it's not a good source. You can try with classical molecular dynamics, use lamps, and you teach how to do that, and after that you can try to use ab initio molecular dynamic, which will be much more costly. But good start, I think it's classical molecular dynamic.
Yeah, basically, if you're trying to calculate diffusivity, for example, as he mentioned, we are using MVT, but before we're doing the calculation, we're starting from a experimentally determined crystal structure. So we got the atomic position, and we relaxed the geometry, and then using the relaxed geometry, we started to do MVT empty simulations. Yes.
So if you do MVT, control how much is stress, because if stress is significant, so it means that you will model different structure, in fact. So you will model structure under pressure, and pressure will modify the vibrational properties of. So there are some papers, if you are interested, for example, how your structure behave under the pressure, so you can control also pressure, but generally it's much more difficult.
Yes, it's very difficult, especially for our system, because our system has about 600 atoms. Is very huge for MD, and if you trying to use MPT, then it will be very difficult to convergent to control the temperature, for example, and we've do very long simulation. So this take a month or so. So so in principle, yeah, you're right. If you're trying to do a smaller system, you can. I think if another way to do this is to say relax your geometry under certain pressure. For example, if you're 1 bar, and then you start from that geometry, and using MVT, if it's very difficult to converge during the empty simulation. So
okay, thanks. Yeah, do you want to address Maxime's question about getting absorption spectrum?
Yeah, so I think there is tutorial on how to calculate vibration spectra on the tutorial of CP2K. Yes, you can do that, and you probably need to set up printing of the electron density, for example, and later on use that data to calculate the spectroscopy. Yeah, but yes, you can do that. Yes.
But maybe some suggestion. There's another approach. You can do static calculation and calculate phonons. And knowing phonons, you can get information about vibrational properties. But I don't know. I haven't seen any example how to calculate phonons by CP2K. But there is some code which is called phonopy or something like this. And from this phonopy, you can call CP2K and probably get the phonons. Because it is the same approach what is used in VASPORs. Doesn't matter, but Abinit has a different approach. But such code like quantum espresso, or you can look at quantum espresso, and simply you must replace quantum espresso by CP2K. But general procedure is the same. And I think it is much cheaper to calculate phonons than perform accurate long molecular dynamic calculation.
Yeah. Yes. Yeah. You can calculate phonons as well. For some, yeah, generally will be cheaper. Yeah.
But phonons under 0K, of course, temperature, yes?
Yeah. So the advantage is whether you need to consider the actual more conditions closer to your experimental condition environment. For example, you have to do molecular dynamic simulations. Okay, so basically I've split my screen, and hopefully you can see this. So if you haven't done so, please just, for example, copy this to your working home directory. So basically it's just work and TA15154 and TA154. Okay, so I will copy this to my working home directory as well, so that we are at the same page. Okay, so and then we have to unzip this. So lots of files, because there are also reference data of previous AIMD simulations. So also some packages, for example, AML, which is used for doing CP2, N2P2 machine learning into atomic potential training, and especially if you're using community model, which I will talk about later. So does anybody have any problem at this stage? So if you have copied data, open another terminal. Okay, so I will get a new one, and you have to grab your port number from the port.txt file inside this folder, CP2K empty training. Change directory to that folder, and for example, if you grab your name, I'm not listed here. For example, my name Lei, port.txt. It didn't have a value, but for you, you should see your name and a 4 digits. Use that number, and in your new terminal window, just sh -l and your number. I will put just 9226. You should use your 4 digits, otherwise you will you might not. Once this is occupied, you won't be able to use this one. Okay, so your username,
So I've just so you know, I've pasted the command, these commands from this slide into the Etherpad in case it's convenient for copying pasting. And Maddie had a question about being a little bit confusing about where to get the. I think maybe it's just a part, Maddie, I don't know, where you get your port number from. There's from this file.
It's you can use any 4 digits in principle, so long as it's not taken. So you don't know what number are people using. That's why I have specified a number for you. But in the future, if you can have a guess, or that number is not taken, you can use that one, for example, for your preferred number, and you can use it for if sometimes it's taken just +1 -1, and it might work, and it will suggest you okay. So I will show why.
I probably should not have assumed that was Maddie. Do you want to? I don't know, Maddie, if you want to unmute yourself and see whether that was the issue, or whether that's just more generally maybe unclear, or whether there's anything else.
So why? So because you were using it here, as you see. You're using it in Jupyter Notebook, and the port is the 4 digits. So it doesn't matter actually in any other cases if you're not, say, tunneling to this session. For example, this one it should. So we don't know the port number we're using, right? But for this one, because we are specifying here, and we will open our browser that accesses data on ARCHER2. So we have to specify this one. For example, if you can, have you already been able to say create your Python visual environment? Because I've already created this one, so I will not do this, but I will show you after you've done this, you can actually source activate this visual environment and started to use the notebook to do the analysis. Okay, oh, I haven't loaded the module, but every time you have to load the module as well. If you're using the visual environment. Okay. Might take a while, but you should be able to open it in your, say, web browser with the linked prompts. Okay, it starts to working. So if you started to run this Jupyter Notebook inside your CP2K training folder, just copy and paste this link. I put it here. Okay. So you will be able to see the notebooks. So if you open this one, on your local browser, you will be able to see this notebook. Okay, so after you've opened this one, I would say you can start to submit a AIMD job in the AIMD folder. Okay, so for example, if you would like to do a equilibration using the velocity scaling, then you can. So I'll check how much time we've got. About half an hour, so we might not have the time to do that. So we just because this system we have, it's not a big system, and we've tested it. We can probably directly go to the, say, MVT folder, and we got a job script, and we also got an input document. So we might need to, say, change the input script a bit on. So basically I've written this as a restart. So most important thing, we have to delete these lines so that it knows it's not restarting a job. And we also need to specify the input file, so which is a and .xyz position, atomic position. So we just copy the equilibration magnesium XYZ to this folder, and we also want to cut the equilibration and sys.imp, because we need to include the cell and the file into our script. All right, and we modify that we put it here. Okay, this should be fine. And yeah, so we have set the wall time to 10 minutes, which will automatically stop. Okay. So let's check the job script again. So probably increase this a bit longer. Okay. And we can now submit the job. So I think I haven't specified the reserve ID as Arno mentioned this morning, but if you use that, you should be able to use the reserved queue. I can't use that one. I will show you the data analysis using my previous runnings on the SAM system, which has a much longer trajectory, and we use that trajectory data to train the machine learned potential.
It's probably tricky because of time. I think we have some requests maybe to slow down a little bit. I think it's difficult. It's just purely, I think, the Python setup probably for some people. Getting the virtual environment installed and sourced and loaded.
Yeah.
And then the second, getting the notebook working. But it's some things. It's difficult to balance.
Yeah, I can see. So basically, I think I'll give you because the job will, if you can play with the submission after the session, I think, if you haven't been able to do that, but if you you can try to set up your environment after the session as well, but I will show you how to analyze the data using the reference data which I've shared with you. For example, if you open this notebook and it's basically all written, all you have to do is change, say, this to your actual file directory, so that it can retrieve your result data. And if you just basically just familiarize yourself with the interface of the Jupyter Notebook, and you should be able to just run each cell and just do very small change on file locations. And also, if you just follow this, and I've also written some text in this notebook that you can read through and have an idea what's going on. And for example, if you check the temperature. It is all inside this system -1.mner file. So basically this just visualizes this file, for example, the temperature, the constant of motion, for example. And also if you've been able to install NGView, I'll show you. So you just read the trajectory, use this notebook, and then if you run it, you should be able to see the trajectory within the notebook, and you press the play button and it will start to move. Yeah, this is the reference data is NPT simulation, because we do need more variation for training a machine learned potential. Okay, so basically, if you've got your simulation trajectory and then you want to calculate the property, for example, radial distribution function, and ARCHER2 has a tool to visualize this. So basically just use the notebook and read your data. But also what you do need to do if you're doing is to set the cell and set the periodic condition for that cell, because when you calculate the calculate the bond length, the distance, for example, the periodic condition has to be applied to your system. So this can be done by, I've already written this, you just follow the comments and you just change your files. For example, your cell parameter results here, and run the cell, and you have to ensure the trajectory length is equal to your cell parameter length. As I mentioned, if you set the print frequency the same in the input script, then this should be of the same length. And you also have to reshape the cell parameters, because when it's retrieved, it's not 3x3 array. So, but this can all be done by follow the notebook. And after that, if you check the cell, it should tell you the cell is already the value set. But before you run this, actually you will get 0, 0, 0, because the trajectory file of CP2K doesn't have any cell information in the data. So that's why you have to do this when you're calculating the GR. So if you check the periodic boundary condition, it is also correctly set for the first image in the trajectory. And if you import this module from ARCHER and you skip the first 1000 frames, for example, and you calculate it using the code, because you want an average, so you can run this by this code, by this one-line code. And after that, you can have a check of the data you got, and you can plot it out like this, like the code here. So this is what you should be able to plot out using your results running from the empty simulation. And if you're interested in the diffusivity or diffusion coefficient of your trajectory of specific atoms, then you should be able to do this by following this notebook again. So because we have run simulations under 1200K of magnesium metal, which is melted. So we can principally calculate the self-diffusion coefficient of that of liquid magnesium. So we read the trajectory data again, and then just follow the code, and you should be able to calculate the diffusion coefficient using just ASE. And you can plot it out and print out the result. Fairly straightforward. Okay, so basically we have half an hour left. So this is the data analysis. So you all get the file. You can play with the notebook later. But at the moment, I will start to introduce a bit to the machine learning based methods in molecular dynamics in CP2K. Basically, there are different options in CP2K. So these three, three of them are machine learning potentials. The PowerML is a bit different. It uses machine learning on the basis sets, I think, and but for these, the rest are all machine learned potentials that you, in principle, are similar, but they all have. So if you're doing machine learning potential, the procedure should be similar, but as the package is different, you will have different, quite different practical usage based on their documentation. So what I've provided today is a NNP, so neural network keyword. So this is basically using N2P2, and this is based on Perinello-Bella neural network potential. So basically it converts a atomic position, which is your geometry, into features using their descriptors, which are symmetry functions, and then fit them into a neural network, and then targeting to the energy, and after you, for example, give enough data and training, and train the neural network, it will give a good accuracy on predicting the energy of the system. And one reason why we're using this this scheme is because it enables the community models, which just uses several models, all of the, for example, 8 neural network potentials, and each of them gives you a energy, and then we averaging the energy as our prediction, and it also gives you a standard deviation. We use that standard deviation as a description of the how the level of disagreement between these members, between these models. We know how important this data is for the training of our potential interatomic potential. This method can actually reduce the data usage, achieving even better accuracy. You can refer to the initial paper published by Christoph. So what we did is, so they actually have a package called AML that can be used to convert the CP2K trajectory file into N2P2 format data. So I actually have a notebook on this as well. You in the data I shared with you. So but what I did is I actually did some modification on AML. So because the initial package didn't just takes constant cell parameters, which means if you're using MVT data, that's fine because the cell parameters didn't change anyway. But if you're using MPT as reference data, then you might have to use this modified AML to be able to convert your data. It's fairly straightforward. I've defined a function. If you, for example, just replace this with the folder, you've run your AIMD simulation, for example, it will automatically write that trajectory into an input file that you can use to train the machine learned potential using N2P2. But of course, you have to install N2P2. So if you'd like to train an MPP yourself, an MP yourself. Okay, so the other session. If you want to use NMP as a force evaluation method, just change the method from QS to NMP. And if you're doing MPT, you have to include stress tensor. But for currently, NMP trained from N2P2, it didn't predict stress tensor, which means we can't use it to do NPT calculation. You can actually run the job, but it didn't give reasonable results. Basically, you also have to replace add this session into your input script. For example, specify where are your models stored. So basically, you have to specify the input of your training script for N2P2. This is for N2P2, and this is scaling data, which converts your input script into descript because you have specified symmetry functions in your input script of N2P2, and then you converted that input data, like using this. If you, for example, if you're using this notebook, then you will get an input data from for the training, and you will convert. You will get a scaling data, which is something like a descriptor that's required for the prediction training of your NMP. So you have to include this as well into your input script, and also you can and then you have to specify your model location as well. So I have for example, we have this example setup file. For example, if you change directory to 600K of MLMD directory, and if you change directory to MBT and check the input script, you should be able to see this, yeah, because we are using MBT models. So instead of using a single model, we include 8 of these models. So 8 of them. All of this is, I think I've shared with you the, let me see. Yeah, so it's not because the time is quite limited, so wouldn't be able to actually go details how these are obtained. But if you refer to AML package, you should be able to have an idea how this was generated, how this was obtained.
Hey, could I
Sorry.
ask a question?
Yeah.
To understand those 8 different models, are those 8 different models 8 different members of the committee, say, that were trained?
Yeah.
Okay, so and you said that doing that committee approach gives you a handle on the importance of the data and variability. Now, how does that translate into the effect that incorporating those 8 models has on the results? How do you sort of do you quantify this somehow, or you just use the committee and that's the best you do and that's it?
So I'm not sure if I get your question correctly. So asking how does this sorry, can you?
Well, I think you answered my question already, actually, which was I wasn't sure whether these 8 models were actually the 8 members of the committee and the committee approach,
Yeah.
and they are. So that was the main thing I wanted to understand.
Yeah, these are sorry. Okay, so basically there are 8 members. So these are 8 committee members of that method. So if you are familiar with that this paper, so you would know there are committee members. Yeah. So basically just followed their method. The first step is just updating the input data, right? You update what data to include using the query by committee method. So you keep, say, do 15 iterations, and you would get a final input data list, and you use that input data and train 8 committee models. And then after that, use that 8 committee models to do prediction. So this is what I am doing. Yeah. So these are different, the 8 committee models. Yes.
Yeah, and the scaling file contains a descriptor. What was that again? That contains a descriptor of what?
So basically, you're in this. They have you have to convert the local environment of atoms into digits. So basically, they use they use symmetry functions to describe that, right? So basically, you set a cutoff and calculate the pair distance and the angles, and for example, and you convert that into a symmetry function, and then do the and then so basically once you converted data, you have to run scaling so that this information is stored as a file that can be used to represent your geometry, and then, for example, to fit into the neural network.
Okay. Yeah. Thank you.
Yeah. So
sorry
basically,
to interrupt again, but there was just a question that Jay asked earlier, which I thought I should point out. It was relating to the material prior to the ML stuff. It's just a question about the conserved quantity. Yeah, he was saying that in the output of the previous exercise, was saying that the conserved quantity in AU what was it? It seems that the total energy, it seems like the total energy, but the summation of kinetic potential is different from that conserved quantity that was shown in the output. So what was the conserved quantity in that case?
You mean this one?
I'm not sure. Yes, possibly. That looks like it does show conserved quantity.
Yeah, this one, because the if you see that the scale is quite small, because this is actually the same thing. This is plotted against the potential energy. This is the constant conservation, constant quantity alone. So this one, it looks like it's not, but actually it is. So if you plot it out together with the potential energy, you would find out that it's actually conserved. I don't know if you're asking this. Yeah, sorry.
Yeah, thanks.
Okay. So basically, we got 10 minutes left, and if you have already, you can try to submit for example, the job using this because the inputs are here. You can just say try it on the 600K and try to get a results. If you haven't, we won't be able to. I don't think you can run a long simulation using AIMD in this session. So you can just use the reference data and plot out the, if you have time to use this machine learned potential to run a simulation. It is super fast. If it's 20,000 steps, it is super fast. You can have an idea, compare with the time it takes on each step. And after that, you should be able to, for example, plot out and compare the radial distribution function together using the notebook and check out does it agree with the AIMD. Here I've using reference data which is NPT. So the orange line, this is AIMD NPT simulation because I didn't run a separate NPT job because it can take some time. While for machine learned interatomic potential, molecular dynamics, I'm using MVT because, as I mentioned, it is not trained to predict the stress tensor. So the stress tensor is not accurate. So it can cause some problem if you run MPT simulations. So I'm using MVT ensemble. But if you compare the data at the same temperature, which is 600K, it looks like it is fine. Yeah. And again, you can use it to run the simulation under 1200K to see if it can reproduce the self-diffusion coefficient of liquid magnesium, if you have time. So basically, the data analysis just need to follow this notebook and change your file directory. Yeah, for the training, you have to refer to. I think Arno has prepared, has put a link in the chat on AML. Thank you very much. And I think you can just follow the link, and there are a bunch of. I think there is an example in that as well. So this one, I don't know why. I think might have to put them. Okay. So yeah, basically there is an example to follow, but again, it might take some. You might have to modify the code in order to make it work. At least this is my case. For example, the run QBC actually, but you can actually, I'm not sure, you can actually start from the, I think start from the AML version I shared with you, because the changes have been already saved. Yeah. Okay, I guess probably there's only 5 minutes left. I will check out if there are some. I see Jay said produce the process for making the SIM and MP files. Yeah, in principle, you should be able to reproduce the machine learned MD using the script I provided to you. So just run jobs based on the input scripts. You should be able to get a trajectory file, and if you're interested, just use the notebook to plot the results out and compare with AIMD simulation trajectory. Yeah. Sorry, I just found the cost quantity. So basically, this is, it depends on what ensemble you're using. If you're using NPT, then the constant quantity is the system thermostat borrow start. But if your NVT is just the system and heat bath. But if you are a MVE, then it should be the total energy of the system.
Yeah, Jay's just asking at the bottom of the chat. He added something at the bottom of the chat. I think the answer is just that you have to. The idea is that you run the AIMD yourself, and that will become the input. But tell me if I'm wrong.
Yeah. So basically, I can share with you the files I'm using, so that you can, in principle, reproduce everything in the, for example, make your own community models. Yeah. Because I have another QBC folder, which is updating the reference data, and that's not presented here because this is out of the scope. But I can share with you if you are interested in, because this is just for empty sessions. But I can share with you. Yeah. Okay, so I guess if there is no further question, I think I can stop sharing probably.
Okay, thank you very much. Nice case study, and then also have a look at how this particular approach to machine learning works. And as I mentioned before, everybody, your accounts will remain valid for a month after the course. And there is currently still about 60 node hours of compute time left outside of the reservation that we have, which ends in 2 minutes from now, I think. Yes. So yes, there's 60 node hours left. It would be great if it's not one single person that just destroys it all, burns it all in one go. I don't know how much the AIMD takes, but you should have a chance to hopefully play around with some of these examples to work with this if you didn't have time to maybe catch up with everything right away and run it yourself and get what was going on at the exact same time. So it's good that we have the examples there. So thanks, Lei. Thanks so much. Then I think, then I think we have a short whirlwind session before the break. Is that right? Yes, I think we have 15 minutes roughly now from Matt about how to do better than basic DFT, how to ascend Jacob's ladder of improved quality towards the heavenly accuracy of whatever it is. Okay, so I'll shut up. Please go ahead.
Thanks for the lovely introduction, Hanno. So let me, I guess I better share a screen, hadn't I? So, these slides, should you want to look at them for any reason, they continue on the same slide deck as I was showing earlier. It's going to be a really sort of flying view as normal. But let's go for it. Right, so the DFT, so there's two bits. You've got to build a Gaussian matrix, which is some sort of description of the Hamiltonian of the system, so how you're describing the different sort of energetic interactions in the system. And then there was a bit about then how we diagonalize it and get the Gaussian functions, the eigenvalues and states of the system. So the diagonalizing it and stuff is going to stay the same, but there are different approximations, different density functionals you can use, different Hamiltonians. I think we had a little bit of discussion about including Van der Waals interactions, which would be important for MOFs. But for other systems, what can be quite important is to include so-called exact exchange. So hybrid functionals are, they're called a hybrid because they're kind of a mixture between a traditional Hartree-Fock approach, which is sort of from the quantum chemical community, and it's sort of the simplest reasonable description of sort of a many electron system. It's got serious deficiencies in the way it treats the correlation of electrons, and it tends to massively overestimate band gaps, for instance, and to cause electrons to really sort of sit tightly and localize. On the other hand, you've got sort of the standard DFT GGAs that were very popular for a long time, PVE, etc. And they had the opposite problem. They tended to underestimate band gaps to allow electrons to spread out, where sort of in reality they perhaps be trapped by sort of lattice potential or something like that. So if you take an average of these two sort of Hamiltonians, sort of 50% of this and 50% of that or something like that, you get something that's reasonable. And in fact, the bit that's averaged, it's not the whole Hamiltonian, it is the exchange part of the interaction. So you have a total energy, which is some alpha, some fraction of Hartree-Fock exchange, plus 1 minus that same alpha, the exchange energy from a sort of a standard DFT calculation, and then the correlation from the DFT energy. There's no correlation in Hartree-Fock. And so it was, you can come up with fairly solid theoretical backgrounds from adiabatic connection theorem where you come up with this, but a lot of the original motivation was really more sort of empirical. As I was just saying, you've got these two extremes. If you average them, you get sort of good properties. So you get much better thermochemistry, atomization energies, heats of formation, lattice constants, Basically, the majority of properties get improved. The downside is that you're introducing this sort of parameter in terms of the amount that you're mixing the two different Hamiltonians together, and there's always a question of how much you should do. There are certain things that you would like. You'd like to fix sort of ionization energies or electron affinities to be the difference of the one electron energy levels. That makes everything more sort of interpretable. And again, there are some theorems that would sort of back that up as the sort of thing that you'd want to do. So essentially, running with these hybrid functionals, this mixture of Hartree-Fock and pure sort of semi-local DFT offers lots of benefits and really sort of orders of magnitude improvement on, particularly for molecular systems, sort of energetics and various properties. Yeah, and band gaps are an example for solid state systems that really come out much better. I'm not going to go into the details, but essentially to calculate this Hartree-Fock term, you need to calculate Coulomb integrals between all possible pairs of basis functions in the system. So there's something that looks a bit like a density from a pair of basis functions and something that looks like a density from a pair of functions. You've got 1 over r, and you get this sort of interaction between them. So where, I don't know if you've looked in the output files, you may have typically thousands to tens of thousands of basis functions. So when you've got the combinatorial stuff of all sort of n to the 4 of those, you're talking trillions and trillions of these integrals that you need to calculate. So you need to do it efficiently. So if you don't do anything, it's n to the 4 number of basis functions, or which scales the number of atoms or the system size. So it would get very expensive very quickly if it was staying like that. There's a bunch of tricks that are pretty much turned on by default. Examples I've given in the that shared folder. Again, I've got switched on. So you can use this sort of Schwarz inequality to ignore certain integrals if some have already been shown to be small. You can also look at the total energy includes, it's not just these integrals, but it depends on how much density there is from these basis functions, how much they're actually contributing to the density of the system. So if the density from those combinations is really small, then you can also neglect some stuff. And if you do that, you can show that actually the scaling for large systems will come down to order n rather than n to the 4. So what you find is actually for small and medium-sized systems, the Hartree-Fock can be really quite expensive. But then as you go to bigger and bigger systems, if you've turned on this screening and stuff, then actually it stops being so much of a problem, and diagonalizing the Hamiltonian becomes the problem again. There are some settings. I said it was a Coulomb interaction between the electrons. That's what you would expect in a sort of how you'd expect electron charges to interact for this full 1 over r interaction, and that can just be specified. This works perfectly for molecular systems. However, if you go to a periodic system, then you run into trouble. If you remember sort of an infinite series, if you've got a 1 over some sort of constant thing, then you get sort of divergence, or at best conditional convergence in series. So To avoid that, there are different functionals that use not a full Coulomb interaction, but in some sense a screened or a truncated Coulomb interaction. So there's a popular functional, HSE, that uses a mixture of error function and complementary error function to cause essentially a sort of an exponential decay of the strength of the exchange interaction, which means that you get rather than a divergent energy, a well-defined energy. The other one that's used quite a bit, or been used often in CP2K, it's something that's probably only in CP2K, not other codes, is this sort of truncated one where you've got the full Coulomb interaction out to some distance, and then beyond that distance the Coulomb interaction just becomes zero. And empirically, if you have this cutoff to be more than about 6 angstroms, essentially you're barely losing anything. But for the same reasons, to avoid these divergences, this truncation distance has got to be smaller than half of the smallest cell dimension, so it can only be sort of half the size of the cell. So you need reasonably sizable unit cells to use these methods. So those are the tricks to do full Hartree-Fock using the full basis that we use for the standard DFT calculation. So this combination of screening, Schwarz quality, screening on the density matrix, and to get numerically stable results, this truncation of the range of the Coulomb interaction, which also allows you to discard centers that are further away. But the basis sets, particularly these MOLOPT ones that I think have been sort of advertised to you previously, contain an awful lot of Gaussian functions, and they become extremely expensive. So actually there is a method introduced in CP2K called an auxiliary density. So again, we've got this full density matrix with sort of nice primary basis, but lots and lots of Gaussian functions. And what we try and do is, instead of having that, we project it onto a smaller set of functions, and particularly functions that are more tightly constrained. So the Hartree-Fock cost goes up massively when you've got diffuse functions that spread out over a long area. You lead to lots and lots of non-zero integrals. But if you can define very nearly the same density from maybe even possibly a larger number of much more tightly focused functions, then you can do some calculations at a Hartree-Fock on that equivalent density matrix instead of the full density matrix. So we introduce this auxiliary density matrix, and we make this approximation here that the difference between the Hartree-Fock exchange in the full and the auxiliary is approximated by the difference of just the DFT exchange in those two. And we calculate the Hartree-Fock exchange only in this auxiliary density matrix. The full details are in the paper there. I'm not going to go into it now. And so you've then got to decide not just primary basis set, but you've got to decide an auxiliary basis set for the ADMM. It's a few bits there. Again, the input file I've got there, it's got an example. There's a bit more about it on the talks from Ghent that I linked earlier. So a follow-up one about the auxiliary density matrix and Hartree-Fock. Yeah, I think given the time frame, I'm not going to go much further than that, but just to say that to make Hartree-Fock in periodic systems practical, you've got to have all this screening, and for the standard basis functions we use, you pretty much have to use this auxiliary density matrix method. There are some new methods using RI resolution of the density that are now being introduced that may supersede ADMM, but I think ADMM is the method for the time being. And I think you'll see Anna using it quite a bit in the excited state stuff as well, as a way of introducing correct Coulomb interactions between the electron and hole in the excited state calculations. So just a quick example, if you calculate diamond's really horrible. It's all super dense, sort of the number of atoms, so you start getting ridiculous number of integrals. So if you calculate the band gap of diamond using just PBE with a primary basis set, then you get a band gap of about 4.2 electron volts. Whereas if you do a PBE 0 calculation, so this is similar but with 25% exact exchange, you get 6.07, which is a much more reasonable number. But to do that, you need to calculate this many integrals. I don't know what that number is, but it's big. So if you do it just with the primary basis set, you get the right result, but it's painful. If you do it just using this auxiliary basis set, then you can see that there's a fairly significant error in the band gap. But if you use this density matrix, this approximation I just sketched out very quickly, then you get a result that's within a few tens of MeVs of the full result. So it's not perfect, but particularly for ab initio molecular dynamics, where you want to be able to run for an extended period of time, and for some systems maybe sort of electron solvated, that sort of thing, where you need these hybrid functionals to get a qualitatively correct description of the system, and it's a very viable method. There's example, I think I'll really just leave this for reference. There's examples around this, a couple of input files in the shared folder. Happy to answer questions later, or even come and spend a bit of time with people that want to run these calculations themselves after the fact. But essentially, you need to add in this auxiliary density matrix method. You need to specify the functional. The full specification can be a bit painful. I put another example for B3lib there. You can actually use this so-called libxc library. Instead of having to specify all of it individually, you can just say use the B3lib recipe from libxc. So you need to specify your functional and these screening parameters that I mentioned. And then you'll also need to specify the auxiliary basis set in the input file. And the thing that's really important if you are running these calculations is to check this stored in core and stored on disk. So the integrals are the same, they only depend on the positions of the atoms, so you don't need to recalculate them at every step of the SCF because the atoms aren't moving, so these integrals are the same. So if you can store them in RAM, then you can access them much more quickly than you can calculate them, at least until we get a proper GPU version. So if you can get them all in memory, then you should find that the first SCF step, when you calculate all these integrals for given positions of the atoms, is quite expensive, but each of the subsequent steps is not really very different. I think this libint library is used to calculate these integrals, so it needs to be installed. It certainly is an ARCHER2, though it's got also a maximum angular momenta that may not be usable for all calculations. I think I've been kicked. I think I've overrun already, haven't I? So I'll shut up. There's examples in the input files there. So if anyone is really interested in running hybrids, I'm happy to sort of have a chat and try and help with that.
Okay, great.
Okay.
yeah, good whirlwind tour.
Yeah, a bit quick, sorry.
That's good. Yes, okay, good. So unless anybody has any immediate questions, this is a good opportunity to take a break, grab a coffee, tea, or temporally appropriate, whatever. And we will recommence in about 15 minutes time, but at the full hour, UK time anyway. All right, see everyone in a bit.
Okay, so thanks, Arno. We thank Matt and everyone, and also the previous talk from Lele. So it was really interesting about the machine learning. Thanks a lot for giving me also the opportunity to give a short presentation here. So as Arno already said, I'm Anna Hina. I'm a junior research group leader at the Christian Albrechts University in Kiel in Germany. And I know Matt because we were collaborating on developments in TDDFT. And so in this talk, I would like to present you these developments that we did and also give you a short outlook on what our current work and on the future features of CP2K that you might want to keep an eye on. Okay, so as I thought, while preparing this talk, I thought that it should be for users who really want to apply CP2K and use the TDDFT module. That's why I would like to motivate the talk also by giving you an overview over the application range that we now have within CP2K for theoretical spectroscopy. So the initial implementation by Marcella and then by Matt was actually published together with an application for absorption spectra of oxygen vacancies in binary metal oxides. And there's also really an impressive list of follow-up work which really show the powerfulness of the TDDFT module for such applications on oxygen vacancies in oxides. While we cannot only compute vertical excitation energies, we also extended the module to compute excited state nuclear gradients. And I'm really happy to see actually that there's more and more work coming up who are using the module to compute emission spectra, as for example within this publication on luminescence of hybrid LED halide perovskites. And I think the most exciting is this relatively new upcoming field to extend the applications from static spectroscopy to the dynamic picture with works, for example, by the group of Bretso and by the group of Akimov, who are now not only computing static absorption energies and excited state gradients, but who are also, based on that, computing non-adiabatic couplings that allow then to describe these excited states, as I said, dynamically, for example, to model the charge carrier transfer in bilayer tungsten disulfide or the recombination dynamics in monolayer black phosphorus. And I think that's really a really interesting new upcoming field, leaving a lot of room for also new developments and an exciting future. And I would like to, with keeping this application range in your mind, now discuss the possibilities that CP2K gives you, going through the applications that I've shown you. So first discussing absorption emission spectroscopy, then a relatively new feature that we just added is to extend the GPW framework to the Gaussian and augmented plane-wave method for the description of excited state nuclear gradients. And I will just shortly in the end say a few final words on current work. And I should mention straight at the beginning that this work was in collaboration, of course, with Jörg and Matt, but also the students that were involved. I would like to thank at the beginning. So Fabian and Belis were working on absorption and emission spectroscopy, and Belis was also involved in this extension to the Gaussian and augmented plane-wave framework. And Jan Roberts' master thesis was on incorporating spin-orbit coupling. Okay, so let's start with absorption spectroscopy. So Matt already gave an introduction to the GPW framework in CP2K, right? So that you already know that we have this dual representation in CP2K in contrast to other plane wave frameworks. We're describing here the density in terms of plane waves, exploiting the intrinsic periodicity, but also in terms of atom-centered local Gaussians. That gives us the advantage of a sparse density matrix. And the formulas that I will show in the following, they will not have all the detailed information on when we're using plane waves, fast Fourier transformation, and so on, or when we are actually integrating using spherical harmonics. But that would make the formulas more too complicated. But you really have to keep this GPW framework and the treatment of periodic boundary conditions in mind. But based on this, we now want to describe the excited state, right? Within the Tamm-Dankov approximation and the Sternheim equations. And what we're doing here is that we're solving such an eigenvalue problem as shown here. So we are diagonalizing an Hermitian matrix A to obtain the corresponding excitation vectors, excitation amplitudes X, and the excitation energies of our system, omega. And this Hermitian matrix A contains several contributions, given here below, a bit more detailed. So the Theros order contributions is just the difference in Kohn-Sham energies, virtual and occupied Kohn-Sham ground state reference energies. And then you have also the first order contributions, which I will always refer to as kernel contributions, which comprise Coulomb exchange and exchange correlation contributions. And in this first part on absorption spectroscopy, I really would like to focus on how we can compute exact exchange integrals efficiently within the TD-DFT module, because I think that's where CP2K is really strong and has quite some interesting features. So regarding the computation of absorption spectra and excited state gradients, you can also have a look at the tutorial, which is online on the CP2K webpage. Just by going to the section optical spectroscopy, you will find a tutorial on how to compute absorption spectra and emission spectra for acetone. And you will also find all the input and output files and a discussion on all the keywords that are listed. Some of them are really trivial. For example, we are solving, as I said, this eigenvalue problem, and we are choosing on input how many states we actually want to calculate. We're doing this iteratively using a Davidson algorithm, and so that we also have to make sure that this algorithm, this iterative determination of the excitation energies is really converged, also appropriately with respect to the ground state settings. If you're choosing a closed-shell reference, you can also, of course, then choose if you would like to refer to singlet excitation energies or triplet excitation energies. So these formulae were all given for open shell references, still having the spin index sigma here. But of course, by just doing a standard spin adaptation, you would have for a closed-shell reference refer to the singlet excitation or triplet excitation energies. And this you can actually choose by switching on RKS triplets to true or false or not. But as I said, I think the most interesting thing here is this kernel keyword. You have two options here. You can choose full, then you would perform a conventional density functional theory computations relying on the GGA or hybrid functional that you would choose within the XC section of the DFT section, as Matt already gave quite a nice introduction to. And when using such a conventional full kernel with a density functional, with a hybrid density functional, you should actually then always rely on this auxiliary density matrix method that also Matt already introduced. But we also have quite a nice second option, and this is to not rely on conventional density functional theory, but to use semi-empirics. And I will shortly discuss the settings for these two options. So if you're choosing this full kernel, I think Matt has already given a lot of instructions that within ADMM, we are not computing exact exchange in the large primary orbital basis, but in this auxiliary orbital basis. And we have different approximations here with the most simplest computing the Conchamp matrix in a very approximate fashion, not including correction terms. And this simple ADMM variant, ADMM2, is actually the only variant that is available for the treatment of excited states, for the computation of excited state energies and excited state nuclear gradients. So you have to keep this in mind, and you should always have the same setting for the excited state as for the ground state. But you can then switch on ADMM by just plugging in the keywords in the DFT section. You should use kernel full to include those exact exchange contributions, first order contributions, and you then should of course choose an appropriate auxiliary basis. The second option that we have is to not perform conventional TD-DFT or TDA computations, but to rely on a semi-empirical kernel. What you're doing here is that you're approximating Coulomb in exchange contributions in these first order kernel, and that you're completely neglecting the exchange correlation kernel. And the 2 electron integrals are then computed relying on the semi-empirical repulsion operator and Lövdin monopole charges. Now, in comparison to original formulations for molecular quantum chemistry, our implementation in CP2K is differing a bit. So, for example, we cannot rely on these Lövdin monopole charges. Instead, because we're using the Sternheimer formulation of the TD-DFT eigenvalue problem, we have to rely on Lövdin orthogonalized or transformed MO coefficients, but we get the same results. Also, exchange and Coulomb contributions, the nomenclature here is different to the original work. So if you know the original work, don't get confused. And you should also, the most important here is, if you would like to choose such a semi-empirical kernel, is that these kernels are, of course, that's why they're called semi-empirical, right? Relying on empirical parameters that you have to choose, and you have to choose them wisely. So the parameters are listed here again. You can actually find them in the code. For example, you have a hardness parameter, which is listed for the whole periodic table. And then you also have these alpha and beta parameters, where we have defaults in the code, but they are parameterized for a chosen hybrid function. And it is recommended actually to change those parameters depending on the functional that you're using for the ground state calculation. So that I would really advise to not use the default parameters here. Also, there's more and more recent work coming up, for example, by the group of Walsh, where they're using machine learning to re-optimize those parameters. And maybe it would make sense to take a look at the literature and use those parameters system dependently or depending on a class of systems, so that you really can achieve such small errors. And then a second thing that is different in our code is that, of course, we're now extending this scheme to periodic boundary conditions, and we're doing this in a range separated way, so that for the semi-empirical short range, we're referring to the semi-empirical operator, while for the long range, we are now using again an exact 1/r Coulomb operator, so that we can apply eval summation. Doing such a range separation, you then have to choose a cutoff. This is standardly, I would say, that here standardly the default is a good choice. However, you have to really keep in mind that periodic boundary conditions in eval summation is just switched on if you do this explicitly by setting the keyword do eval in the corresponding STDA section. But doing so, you can then perform a TDA computation to get excitation energies and oscillator strength. There are a lot of other keywords still available, and that you can have a look when going through the manual. For example, the dipole moments, of course, you should always keep in mind here that you have to choose the correct representation. For example, if you want to treat periodic systems, then you should choose either baryon or velocity representation. We applied this implementation for a set of covalent organic frameworks shown here. So what you see here are absorption spectra for ADMM shown in red compared to the SCDA spectra in blue. You get an overall qualitative agreement. And most importantly, what you see is that we are quite fast with this approximated hybrid functional for unit cell sizes of 300 atoms and for broadband spectra of 500 excited states. And we gain roughly an order of magnitude when also switching to the semi-empirical kernel. However, then you get errors of roughly 0.3 to 0.4 eV. All these data for these computations that are referred to in the publication are also archived on Materials Cloud. So I always tell the students to have a look at those archives because they contain all the data. And if you would like to perform such a computation on a covalent organic framework, you can also take a look at those input files stored here. Okay, with this, I come to excited state nuclear gradients. So the second part. So far, we just discussed vertical excitation energies. But if we would like now to describe emission, we have to optimize the excited state because the potential energy surfaces of ground state and excited state might differ. And it is therefore really important that we extended the TD-DFT code to excited state nuclear gradients. But I hope I can convince you that we now have a code which allows us to do such computations very fast. For example, here the timings given for such a solid for fluorescein, which is a dye used to color rivers green, as you see. Okay, so the computation of excited state gradients. What do we have to do in addition to solving the eigenvalue problem that we have already seen at the beginning? What we have to do here is that we have to choose a formalism that allows us to avoid what we call the first order response. So the perturbation of the MOI coefficients with respect, so the derivative of the MO coefficients with respect to the perturbation. Just taking the total derivative straightforwardly would really include such a term, and this would be really costly. So what one is doing then instead, and how the implementation in CP2K is performed, is that one is using a variational formulation, setting up an energy expression which ensures that the total derivative can just be computed or is just given by this first term in this expression here above. Making sure that the energy is variational with respect to all parameters can be achieved by including stationarity conditions via the corresponding Lagrange multipliers. One stationarity condition is that the ground state equations are fulfilled, and a second constraint that you always have to take care of is that you have to take into account the geometry of dependence of the atomic orbitals. So within CP2K, we're relying on the GPW formalism, right? We are using Gaussian orbitals, and in contrast to plane waves, these are dependent on the positions of the nuclei, so that we really have to take into account that the overlaps of Gaussian orbitals and so on change when changing the position of the nuclei. But when setting up such a Lagrangian, we gain a more efficient expression. In return, we have introduced Lagrange multipliers, and so that we now have to compute a set vector equation to get the Lagrange multipliers so that we can finally compute the forces. One more thing, if you're interested in more detail in this, in the equations and in the derivations, so that's a very rough sketch, right? But if you're very interested, you can also have a look at the paper. I think what is interesting here, or what we could show here, what is really interesting is that you need to take into account different orthogonality constraints for the different orbitals that we're considering, ground state orbitals, response orbitals, and so on. And we could show that you don't always have to introduce them via constraints and new Lagrange multipliers in the equations, but you can instead sometimes use projection operators on the virtual space to express or to ensure those orthogonalities. But coming to applying or to the computation of excited state forces, so what you have to do now is to switch the energy keyword to a force keyword or geop keyword. If you want to use ADMM, you should always include the ADMM kernel correction symmetric keyword, and you have to choose the excited state that you actually want to optimize. In the output, you will then see that you are solving, as I had on the slides before, first this excitation eigenvalue problem. You get the excitation energy or the energy of the excited state, and then you're iteratively solving the Z-vector equation to get the final optimized geometry. This linear response, this Z-vector equation is solved iteratively, as I said, and if you're having convergence problems, you can also include a linear section in the TD-DFT section to optimize this. As output, you will then get the atomic forces, and you can also include print statements to get more details on the geometries. And here's a benchmark that we have actually performed to compute fluorescence energies. So on the left, you're still having vertical excitation energies, but in comparison on the right, you're now having here the emission from the first excited state for conventional hybrid functionals, PV0, compared to the ADMM approximated ones, to the semi-empirical STDA kernels in comparison to conventional density functional theory. And I think it's really astonishing that also the semi-empirical kernel is giving quite reliable results. So overall, what you can keep in mind is that you should always use ADMM. I think Matt already said this. And with STDA, you have to be a bit careful with choosing the parameters, but it's quite fast, and the errors are still, I think, in a good range, both for geometries as well as for excitation energies. And yeah, here's again final motivation for this semi-empirical kernel, showing timings for this covalent organic framework for the computation of 10 excited states or one excited state geometry optimization. And you see that if you're going from conventional DFT to ADMM to STDA, you always gain one order of magnitude. And with this, I come to the last point that I would like to spend most time on, and that's the extension of the GPW framework to Gaussian and augmented plane waves. So as I said in the beginning, in CP2K, we're relying on this GPW framework, but we just recently extended the excited state gradient implementation to GAPW. Matt also gave an introduction to this, so I won't spend much time here. But just to remind you, so in GAPW, we're trying to also capture the heavily fluctuating density at the atomic cores, which is not directly accessible or at a reasonable computational cost with plane waves. And this is done by separating our molecule into atomic and interatomic regions. And that this separation of the density is reasonable and giving the exact density is ensured using Blöchel's idea of using projection operators. The extension to excited state gradient, so here on the right, you also see again this sketch that we're setting up a variational Lagrangian, then we're solving the Z-vector equation to get our Lagrange multipliers, and then finally we're computing the forces, is in principle exactly the same as for GPW, except that we really have to introduce this separation into atomic and interatomic regimes, and we have to be a bit picky about ground state densities to discriminate ground state densities from excited state densities, because the ground state densities still include core compensation charges from the Ewald summation. But these are not very important details. The equations can all be found in the paper. What is maybe important for you is that you can now really switch from GPW to GAPW in CP2K to compute excited state gradients. This allows you to perform all electron computations. You can choose a smaller grid. And what you have to be careful about maybe is that when choosing the atomic basis sets for the atomic regions, it is standardly recommended to refer to the orbital bases and augment them with adding a few more primitive Gaussians, as you can do with this GAPW1C basis keyword. And for now, we just applied this, for example, to computing a defect in hexagonal boron nitride. We could show that for this defect, the emission from the first excited state, so-called zero phonon line, is in good agreement with highly accurate GW and BSE data or with experimental data. And most importantly, so I think what is also interesting is, as I said, that you can now perform all-electron excited state gradient computations. And with this, you can also compare with molecular quantum chemistry codes, for example, with codes like Gaussian. And here the errors given for energies and forces for the ground state, singlet excitation energies and triplet excitation energies. And what you see is that errors are really small and the codes are really well comparable. And with this, I would just add a few more words to still ongoing work. So the following slides are all unpublished, but it's hopefully coming soon and is ongoing work in the group. And what we're trying to do here is really to extend the TD-DFT module to covering more photochemical processes. So what you see here on the left is a Jablonski diagram that you know, right? And what we discussed so far was the vertical absorption energies as well as emission. However, so far we were only discussing fluorescence and not how singlet and triplet excited states could interact, so that we also gain access to describing phosphorescence. I had also on the first slide that we, when choosing a closed shell references, are getting access to singlet excited states and triplet excited states, but we're still missing their interaction and also the description of the triplet states with a spin angular momentum quantum number of 1 or -1. And to get access to all those triplet states and also to describe the interaction and to describe photochemical processes like phosphorescence, we have to include spin-orbit interaction, spin-orbit coupling. With conventional DFT, we cannot capture those or describe those triplet states, but there was a suggestion by Tavanelli to do this using auxiliary wave functions, which are described such that creation and annihilation operator are now referring to corresponding response orbitals that we gained from a previous TDA triplet or singlet computation. When doing so, you can set up these wave functions, and then you can also describe the interaction in a perturbative fashion, so just as an additive term to the TDA energies that we have discussed so far. And for this, to compute the interaction, you can at the moment in CP2K choose different one-electron Hamiltonians. One that is based on Van Buren's model potential within the zeroth order regular approximation. And if you don't want to perform an all-electron computations, really treating all electrons explicitly in the valence region, you can add also pseudopotentials, so corrected pseudopotentials, as they were published by Hardwickson. Yes, and in the code, so if you would like to switch on spin-orbit coupling, you can then just add a keyword and a print statement to also print out the corresponding energy splittings and the spin-orbit coupling elements. And the SOC corrected pseudopotentials were just added recently by Matthias Krack. You can also have a look at them there in the data directory of CP2K, and you have to make sure that you're also referring to them in the DFT section. My master student then did computations for a molecular test set as shown here, and compared those to really highly accurate DFT MSCI reference data of crystal Marian. And what is shown here, for example, in the middle, are correlation plots comparing our DFT results with this DFT MSCI data for energy splittings and spin-orbit coupling matrix elements, and we get quite a good agreement. So I think that this is on a good way, and we hopefully also have it finished soon. And with this, we also would like to now go towards this dynamic description of excited states. As I said in the beginning, I think that this is really an exciting new field. that is coming more and more up also for solids and surfaces implying periodic boundary conditions. What you want to do here is that you don't only want to describe vertical absorption going from the ground state to the excited state, or the reverse emission from the excited state and the ground state, but you also want to track the dynamic evolution of those excited states following the potential energy surfaces. And for this, you have to really describe the interaction between excited states. And you can do so by setting up such a linear combination, including all the wave functions of all the excited states. And if you plug this wave function into the time-dependent Schrödinger equation, you actually see that to get such a picture and the interaction of the states, you have to compute what we call non-adiabatic time derivative couplings, as I have already mentioned them in the very beginning when talking about the work of Bredstow and Akimov. When propagating the nuclei also classically and hopping from the surfaces, you're standardly referring to the algorithms as trajectory-based surface hoppings. They are relying on a stochastic hop from one surface to the other, which is computed based on those couplings. And there are different formulations. I won't go into detail with this, how to compute those couplings. And it is therefore, because there are so many formulations and also so much that you have to consider most quickly or most efficiently actually to ensure such, or to go, if we want to go for such a dynamic description, to enable such extensions by just setting up an interface. And we did this with CP2K and Newton X, so that we now have access, our current work is now to gain access not only to excitation energies and its excited state gradients, but also to non-adiabatic couplings. There are semi-empirical couplings which actually come for free. And so there's already a tutorial on the web page which goes through this, how you can actually perform such calculations to obtain, for example, such a broadened absorption spectra as shown here for pyrocene. Here we exploited this extension that we actually now have from going from GPW to GAPW to perform an all-electron computation to compare CP2K with the molecular quantum chemistry 202 mole. And for pyrocene, we get a good comparison with respect to the work of Mitrich and also with experimental data. And you can have a look at this tutorial. So it also goes a bit more in detail over the theory, and then also gives you instructions on how to set up the input files and on how to perform such a calculation. And also discusses then, of course, the outputs. And it is also recommended really to take a look at the Newton X tutorials. They're quite extensive, and it's quite a nice documentation, really giving you an overview of all the features that you can use with Newton X. And with this, I'm at the end, and I would like to thank you for your attention. Thank you very much.
Okay, great. Really interesting. I mean, it's for somebody, I'm just thinking of people who've not used CP2K before, starting off with getting introduced to some of the basics this morning, and then seeing going from standard DFT to hybrid, and then seeing all of these new developments. What can be done now, what is starting to be able to be done. It's really, really exciting. Where have you seen some of the most sort of enthusiastic interest and uptake from the particular areas wanting to use these new DFT methods that you're implementing?
So yeah, as I said, I think it would be quite nice now to extend this to do non-adiabatic molecular dynamic simulations very efficiently on the large scale with CP2K. So there are already some interfaces existing, but they're also making approximations to couplings and so on. And I think there's still a lot of room compared to what you have for molecular quantum chemistry. So there's much more available for molecular quantum chemistry.
Yeah, I would encourage everybody to ask questions. There's a question from Maxime. I don't know if you can access the chat and have a look, or if you would like me.
Yes, I'm new to Period. I want to investigate. So actually, so far we don't have, yeah, it's a question about excitonic coupling, right? So far we are not having, including any dynamical screening. It's a nice question. Yeah, so one of my PhD students is actually working on extending this to describe excitonic effects within the Betis-Salpeter equation, or within a semi-empirical approximation to the Betis-Salpeter equation. So hopefully, so I have not included this yet, but he's already working very much hard on this, and hopefully we will also succeed and that soon, and that this will then be a future feature in CP2K, so that you can also treat excitonic effects, and then also have maybe go all the way from excited states, excitation energies to gradients to couplings. So this would of course be the challenge then, yes. And then the next question is, triplet state a well-defined electrons in the same way as molecule? So I think if you're, I think that's a question that if you're referring to a closed shell wave function where the Hamiltonian is commuting with the spin operator, right? Then your wave functions are eigenfunctions of the spin operator, and then you actually have a wave function which is corresponding to a spin multiplicity. So then you can talk about singlet or triplet wave functions. And that's why when having closed shell references, and we are having this feature that our Hamiltonian and so on are eigenfunctions or commuting, and we have eigenfunctions of the spin operator, that we have singlet and triplet wave functions. Now for periodic systems, this depends a lot, right? So for example, if you're then switching to solids, you might not have such an easy electronic structure, right? So that it will be hard to speak about singlet and triplet wave functions in the way I did it in the talk. If this is answering the question, I'm not sure. But yeah, so I think for more complicated electronic structures, I mean, then it's just not defined in such a way as it is for a closed shell reference.
I can suggest, Kuzen, if you want to unmute yourself and just respond directly, if that answers your question or not, that could be useful.
Oh yeah, sure. Can you hear me?
Yes.
Yeah. Thank you so much for your talk and the answers. So yeah, so my concern is, if the periodic system is a molecular crystal, like you can extract the isolated fragment from the periodical environment, then probably we can still define the single and triplet from the fragment, right? Because each fragment is like an individual unit for this photo response. But you also mentioned if it's a solid, it's a continuum and a band structure, then maybe it's difficult to define whether it's a closed shell or it's open shell. So in that way, I'm not sure if we can still compute the the phosphorescence as we did in the molecular system.
So this was a lot. So I first of all, so the current implementations for spin orbit coupling is just implemented so far for shell references, but we are planning to extend it to open shell references, and then you can also still set up wave functions where you flip the spin as it was shown on the slides, right? Where you create an excited state where the spin, where you still have alpha beta spin combinations, so that you would actually get a singlet excited state or the corresponding triplet excited state. So we are planning actually on extending the implementation to open shell references. For this, however, we need to take into account spin flip excitations, and this we have not achieved yet. So, but that's also ongoing work. But it's so I don't think that it has something to do with fragmentation or also not continuum states. So I was just so but or I don't see this, but the plan is also, of course, that or you can also, of course, treat open shell systems. Yes. So maybe this was irritatingly described. That's true. And then talk about singlet and triplet excitations. Yes.
Yeah. Thank you. Thank you for the answer. Yeah. So maybe an extension of my question is, so we imagine in the unit cell, if there is a unpaired electron due to the spin flip, then because of the periodic boundary condition, so for the real system, there will be infinite number of unpaired electron. I don't know if it's that's a physical picture of that. So imagine some electron is excited then because it's periodical. So we always use finite cell to represent the infinite system. So in that way, we actually imagine all this, there are infinite unpaired electron. I'm not sure if I think it's right or not.
So it of course one of course has to check that the unit cell is chosen large enough so that you don't have and you have to see how large, for example, your exciton is or so. Of course, yes. So I'm asked, a lot of people ask this question when I'm giving talks. So I think this has to be checked carefully, that you're including a large enough unit cell so that if you're looking at a local excitation in a large molecule, that you're actually capturing this local excitation and that it's not interacting with its replica when including periodic boundary conditions. Yes, I agree. So one surely has to do some benchmarks or to check this very carefully when setting up the computations. That's true. But in principle, I mean, we can choose then the unit cell large enough so that we don't have this interaction with the replicas. So I don't see, a problem in this.
Yeah. Thank you again.
And can I encourage Maxime, if you want to do the same and just say if that answered your question previously when Anna was responding to your question.
I'm not sure, to be honest, because I'm quite new to working on periodic systems, so that's why maybe my question is super naive. But because doing some literature work, I found that if I want to see the exciton coupling, if I look at an absorption spectra obtained with TDDFT or GWBSE or whatever method we fancy, I've read that you have to use GWBSE to see this exciton coupling. But I was wondering if we use a hybrid TDDFT method, we have a non-local TDDFT method, and then maybe we can get that. Maybe it's naive and something I didn't understand, but
that's what I tried to say, right? So I just a comment again for the other question. So if you don't want to describe local excitation, but for example plasmons, then we actually want to consider periodic interaction, right? Just with this, but now coming to your question, that just came to my mind. Sorry. Now coming to your question. So with this excitonic effects, they just covered within GW and BSE. So there are papers showing this very nicely. And there's also lots of papers by Neaton, for example, showing that you need dynamical screening as it is introduced only in GW and BSE. to get, for example, the image charge effect and so on. So and excitonic effect. So we cannot capture this. So there's, for example, a paper also by ARCHER2 where they're showing that you really have to go to GWBSE, and that hybrid functionals are not good enough. So it's not just GGAs, it's also hybrid functionals that capture, that, for example, don't capture this dynamical screening.
Okay, all right, thank you.
Was this answering the question now? Okay.
Yeah, yes, yes, in fact, yes, thanks.
Okay, do we have any more questions for Anna? Doesn't seem like it. So, well, thank you again very much for a very interesting talk about future directions as well. And so in the schedule, what we had planned for now was really an opportunity for more general Q&A. The idea was that, have people having, everybody who's attending and is stuck with us as well through the day, what you came looking for in terms of figuring out how you can use CP2K for your own research, whether you should try and what to consider. Just if you have any questions that you're wondering about, now is an opportunity to ask some experts in the virtual room, not myself, but the real experts, about any recommendations, advice about what to be careful with, what to watch out for, yeah, or anything else you're wondering about, really, CP2K related.
Yes, well, I have a question, if I may, yes.
Go ahead. Yeah.
Because I was wondering, I don't know if we can do this in CP2K, to be honest, but talking about AIMD earlier made me think of that. Because also I am wondering if it's possible to obtain the I'm still interested in absorption spectra in general of periodic system, and I was wondering if there were a way to consider the vibronic coupling in the absorption spectra. So because we talked about AIMD, so I was thinking if we use an MD AIMD scheme, we would have the vibrations of the system, I guess, and then I was wondering if from that we could go up to a vibrationally defined absorption spectra using TGDFT. It's a complicated question, but that was something I was thinking of and wondering if it's something possible, maybe with some tools in CP2K. I don't know.
I'm not an expert, but I think the ab initio stuff, you've got the wrong weighting of the excitations, because they're classical vibrations rather than quantum. So I think you'd have to actually calculate phonons and then get some weighted distribution of phonon states. So there is a thing that was done there to give initial guesses for molecular dynamic stimulations, which was again this weighted sort of normal mode analysis. So I think something along those lines is possibly possible, but
because I know some methods exist for molecular systems and not periodic systems using Fermi-Golden rule based approximations from the Hessian. There is a calculation of the Hessian, etc., to get the vibronic coupling and the vibrationally defined spectra. And I was wondering if there was something in CP2K or else to get that on a periodic system. But I think that's a really complex problem. But yeah, okay.
Okay. Right. Anybody else?
But so regarding that question, so about this vibrational resolve, so you mean that you get the band broadening, for example, in absorption spectra, right?
Yes, getting the broadening is what I would want to
So,
get.
that's what I tried to present in the end, right? So what one
Yes.
can do is such a what they have in NewtonX is a nuclear ensemble approach. So what you're doing there is that you're just computing a vibrational spectrum with CP2K. So just the second derivative, the Hessian, you just print the normal modes and you read them in, and based on a Wigner distribution, you're then generating an ensemble of geometries and velocities. And based on this nuclear ensemble, that's why it's called nuclear ensemble approach, you can then compute a broadened absorption spectrum.
All right. Okay.
It's straightforward.
Okay.
And this
okay.
is
Okay.
also, there was not much that one needed to do. So in principle, it was just that you then lack rotational degrees of freedom if you go into periodic boundary conditions, right? And we had to change stuff there. But in principle, it was already all provided with NewtonX. So that's also provided for periodic boundary conditions.
All right. Okay. Thanks. I'll have a look into that. Thank you.
While potentially people are thinking of something else to ask, I remembered Dimitri's talking about QMMM for biomolecular simulation. So I've just put in 2 links for best practice guide, both for specifically using CP2K with GROMACS for QMM, things to watch out for, and also a guide for sort of more methodological approaches that are sort of agnostic to CP2K, but more generally about QMM with biomolecular simulation, and the workshop that I was involved with in organizing the project by Oxel that really talks about discusses some of the choices and things, how to be careful with regards to choice of functional in certain situations, and also how to choose the QM region, how to deal with interactions, etc. So that might be useful. I saw there's another question from Maddie. Yeah, is that clear, Maddie? Feel free to unmute if you want to say yes or no, or even just clarify if it makes sense. Or not? Okay. Well, in that case, it doesn't look like we really have a flood of questions, but a nice discussion, I think, about the last talk, a couple of general questions. So I think, in the absence of any questions, really, that we can probably wrap up a little bit ahead of time. So I would like to thank very much all the speakers who contributed, Matt, Anna, Lele, and San Young in the background as well, supporting that very much. I hope you found this useful, attending this. The sort of more basic concrete materials that we started out with this morning are still there to refer back to. It's a sort of simple summary, and it walks you through. I think it's nice because it's walks you through some exercises that are of the kind that are also exercises on the CP2K website. But I think it's often using the same very simple H2O system. So maybe it's sort of quite a nice sort of basic concrete thing that you can run without taking too much resources as well. It's quite small system. So maybe even if you don't have access to HPC, then you could run it on a smaller system. But if I repeat myself again, I will do it. Then you continue to have access to ARCHER2 for a month. And let me just check to see if anybody has completely used up all the time. It looks like we have plenty of time left. So we have about 60 hours, 60 compute node hours left of time. So feel free to play around with any of the exercises, input files. And if you have any questions, I'm sure the people who provided them will be happy to follow up and get in touch. But other than that, thanks everyone for attending, and I wish everybody a good rest of your day.